In the previous video, we defined the limit of a function and computed an example. Let's see now an example of a function where we can't find its limit. So let's do the same thing as we did in the previous video, but now with this function g that is defined piecewise. So the function is 1 when x is greater or equal than 0, and is 0 when the value of x is less than 0. So in this case, filling the tables should be a bit easier. So pause the video and try it on your own, and then we will do it all together. Great. So in this case, when x is greater than 0, the value is constantly 1. So all this table will be equal to 1, the value of the function. And in this case, the value of the function will be always 0. So notice that when I approach 0 with values that are greater than 0, the function is getting closer and closer to 1. But if I do the same thing now with values that are less than 0, my function is getting closer and closer to 0. So in fact, in this case, our function is not approaching a single value when x is getting closer and closer to 0. So in this case, we say that the limit of g as x approaches 0 does not exist. And we usually write this when this is the case. D and E as in does not exist. Even though the limit does not exist in this case, the function g was not that bad. We could clearly see that it was approaching 1 from the right and it was approaching 0 from the left. So that motivates the following definition. We can also talk about limits, but only considering values from the left or from the right. To denote this, we will add this small negative sign when we refer to values from the left, and this small plus sign when we refer to limits from the right. So what is the main difference between this definition and the definition of the limit is that we are restricting our view to only values that are less than a for the limit from the left, and we're only restricting to values that are greater than a for the limit from the right. So let's go back to our function. So notice that in this case, when I take values that are less than 0, then the function gets closer and closer to 0. And in the same way, if I take values that are greater than 0, then the function gets closer and closer to 1. In fact, they are constantly 0 and constantly 1. So it's even easier to see what the limits from both sides are. Then in this case, we can say that the limit of g when x goes to 0 from the left is equal to 0, and the limit of g when x goes to 0 from the right is equal to 1. So remember that we started this video saying that the limit of this function did not exist, right? So we write it like something like this. And also we can see that in this case, the one-sided limits are different. So this will be the content of the first theorem of this class. The theorem says the following. The limit of a function f when x goes to a is equal to L only if the following holds. So the limit L is in fact a finite value. This means that the function has to be approaching a real value and not going either to infinity or negative infinity. And the other condition, which is the most important one, is that the one-sided limits, so that means the limit from the left and from the right, have to be equal. So this is what is written here. The limit from the left and from the right are both equal to L. One final comment to make is about the relation between the limit of a function and the value of the function at that same number. So the fact is that this might be different or equal. So we say that they're independent. That means that when the limit exists, the function might be the same as the limit, the value of the function might be undefined, or the value of the function might be defined but different than the limit. So those three cases might happen, and we will see examples of those three cases. In the next video, we will end the section of limits, introducing some properties that will allow us to compute these limits easily.